Section 8.6, equations in polar coordinates and their graphs. Basically, we're going to graph equations here. We'll look at the important parts, important stuff, and see how we do this. So when we have equations in polar, they're going to be written as r equals f of theta. This means r as a function of theta. So theta will be the variable here. And we are going to start by learning how to graph using what we learned in the previous section, something like r equals number, say 2, r equals 2. When they say r equals 2, I don't see theta here at all. So I'm going to form XY chart, or here we call it r theta chart or theta r chart. So theta here, what is theta? What is theta for this? I don't know what theta is. Can it be anything? Yes. Say 0. You want to put like pi over 4, maybe pi over 2. So what I'm doing, I'm picking points. I picked this, I picked a point here, I picked a point here. I can pick a point here, the 2 pi over 3. I can pick the pi, and see what happens up to this point. What is r? R is always 2. That's what this is saying. R is always 2. By just going up to pi, let's see what we get. When we want to plot, this is the first point, 0 comma theta. So the r is 2 and theta is 0, right? So 0 means it's 0, and this is 0 degrees. This is 0. So you're gonna go 1, 2. That's the 2 here. The next one is pi over 4 comma 2. So we're gonna go pi over 4 as we did before, and 2 on this. The next one, pi over 2 and 2. So that's pi over 2. Then 3 pi over 2, 2 pi over 3, 1, 2, pi, 1, 2, and then we can continue with this. Like if, let's say, you take 3 pi over 2, which is down there, r is 2. So no matter in what direction you go, you're going to always go 2 units, 2 units, 2 units. Even if you continue this way, 2 units. So what we get here is we just have to connect them. And notice that gives us a circle. So it is a circle with radius 2. With radius 2. So that tells us in general, when someone asks me to graph r equals number a, let's say, then it is a circle with radius a. With radius a. With radius a. So that's what we have here. What about if we graph theta equals pi over 4? Not just like r equals number, but what about theta equals number? How is that going to look like? Well, okay, so you can do r theta or theta r, it doesn't matter. If you want to do theta and then r is fine. So let's see what we have here. So theta is pi over 4. This means it's always going to be pi over 4, pi over 4, pi over 4. That's for theta, pi over 4. It doesn't matter. So r, it can be 0. You can take it 1, 2, 3. Even if you want to take -1, -2, it's fine. And now what we have to do is just plot this on the graph. Let's see what we get. Pi over 4, 0. So this means angle pi over 4. This is pi over 4. That's the positive axis. And 0 is just there. Pi over 4, 1. It's here. Pi over 4, 2. Here. Pi over 4, 3. -1. Well, you have to extend it the other way. -1 here. -2 there. So what do we get? We get a straight line. A straight line. Making pi over 4 angle with polar axis. With the polar axis. That's the next one. That's a common one. So always, in general, we can say, in general, theta equals a is a straight line. Throw the pole. and makes a angle with the polar axis. How about if they change it to a different one? Let's say they ask us not just r equals number or theta equals number. Let's say r equals 2 sine theta. 2 sine theta. So again, we're going to take values for theta and corresponding r values. Get the corresponding r values, theta and r. So here what we have, what angle theta you can pick? 0, pi over 6, pi over 2. These are coming from the unit circle. 5 pi over 6, which is 150, and then 180, 240, 270, 11 pi over 6, and then 2 pi. If we substitute that in, sine 0, 0 times 2 is 0. Sine pi over 6 is 1/2. 1/2 times the 2 is 1. Pi over 2, sine pi over 2 is 1 times 2, 2. Sine 150, sine 150 is also 1/2 times 2 is 1. Sine pi is 0. 4 pi over 3 is negative square root of 3 over 2. So that's negative square root of 3 because 2 times this. This 2 is coming from here. 3 pi over 2, sine 3 pi over 2 is negative 1 times 2 is negative 2. 11 pi over 2, the sine is negative 1/2 times 2 is negative 1, and the 2 pi is 0. So then what do we get? So 0, 0 is there. I know it's not going to go anywhere. Pi over 6, so we draw pi over 6 and 1 is there. Pi over 2 and 2. 5 pi over 6, which is 150, and you go 1 only on that. The pi, it goes back to 0. Now the next one, 4 pi over 3, that's 240. 240, maybe something like this. 240, and on the 240 we need to move on negative rad 3, so that's gonna go in the opposite direction here. 3 pi over 2, which is 3 pi over 2 here, that's 4 pi over 3. We're gonna go back to negative 2, so it's gonna be here. And the other one, 11 pi over 6 is here, so but the opposite direction, 11 pi over 6, it's gonna land here, and 2 pi over 2 pi is 0. So it started here, went all the way up, down, and then it went through this again, like through another cycle. So if you add more points, it's gonna keep moving around and around. And in fact, this is a circle. It is a circle located in the upper half plane. With diameter 2. In general, this is what I want you to know. When someone asks me to graph things like this, I know how the graph's gonna look like without showing any step. So if we have in general r equals a sine theta, there are two things can happen here. Depending on a can be positive or a can be negative. If a is positive, it's going to be a circle in the upper half plane, like so. And if it's negative, it's in the lower half plane. Upper half plane, lower half plane. With diameter a. So this distance is a. This distance is a. So if you look back, compare this to what would they give us, it was 2 sine theta. So it was a circle in the upper half plane with diameter 2. So the center would be 0, 1 or 0, negative 1. So this is important to know. Now, does that apply to cosine in the same way? Yes, it does apply to cosine. So if I want to look at r equals a cosine theta, how does that look like? Well, there are two cases again. If A is positive or A negative. If A positive in the cosine case, this is only cosine theta, not 2 theta or 3 theta. Everyone has a different shape. This one is going to be also a circle in the right half plane. So if A is positive, it's going to be like this with diameter A. If A is negative, it's a circle in the left half plane. Like so. So sine always going to be up or down, like upper half plane, lower half plane. Cosine, right or left. Right or left. So if they ask us to graph, let's say R equals 3 cosine theta. Without even plotting points, we can graph it right away. That's cosine is going to be either to the right or left. Since it's a positive, it's going to be on the right side with diameter 3. So this is 3. That's what it is. So if it's negative 3 cosine theta, then it's on the left side. It's on the left side. And you can run points and see you will get the same one. Other shapes good to know. Let's say if R equals A plus A sine theta. Okay, here A is positive, I'm going to assume. So this will be what we call, it's going to go like this. Sine means up or down, so it's going to go like this. This is called cardioid. It's like upside down heart. Cardioid. And this here, depending on A, that's A comma 0. And this always 2A comma 90 degrees. So depending on A, if it's 1, 1, you go 1 this way and 2 up. Now what about if it's negative? So R equals A minus A sine theta. So still sine, but negative or minus is going to go down. So it's going to go exactly like a heart, down. So it starts this way, down, up. So this is again A0, and then this is 2A and 3 pi over 2 or negative pi over 2. So this distance from here to here is 2A. 2A distance. So that's for cardioids. Are there any other cardioids? Yes, in case of cosine, it works the same way. I'm going to do this, and I'm going to do A minus, not just A plus, to show you how the cardioid works. So this is what we have. It's going to be, because it's positive, it's going to go to the right, like this. This is 2A distance, this is A, 0, like A 90 and 2A 0. For this one, because it's minus, again, A is positive, its minus is going to go to the left. So that's why it's going to be to the left. It's called cardioid again. It's to the left because it's minus. So sine or cosine, always right, or sine, up, down, cosine, right, left. Cosine, right, left. So if you want to see, let's say y equals 1 plus sine theta, and then graph r equals 1 minus cosine theta. Or if you like, we can put 2 here and 2 there and see. Imagine A and A's, they have to be the same here. If they are not the same, the shape will be different. So 1 plus r, 1 plus sine theta. 1 plus sine is going to be up or down. But it's a plus, means it's going to be up. And then here, there's a 1 there. So this means that there's a heart that opens this way. Like this. This is 1, this is 2. See, it's 2 because 1 plus 1, 2, and A here is 1. So for this one, that's a cardioid. It's a right or left because cosine. So cosine tells me either left, comma right. But the minus sign tells me it's going to go to the left. So it's going to open to the left, like this. And then you can label the points. A is going to be here, which is 2, and this is 4 because it's double A. So that's how we graph them. Now, one thing we can do is, you can just remind you, Desmos is really good resource to graph these ones. And then play around with the numbers. Make it 1, 1, 2, 2, or 2, -2, 3, -3, 3, and then see what changes is happening. That's a really important tool to help you, especially in graphing polar coordinates. What other figures would be good for people to be familiar with? What about if it's not just r sine theta, it's r sine 2 theta or 3 theta, what's going to happen? So let's say sine 2 theta. Sine 2 theta, this number here, this is going to go, we call it rows. It's going to go rows. But the rows has leaves, like how many leaves is going to be. The sine always going to go like this. It's going to go in the quadrants, in the middle of each quadrant. In this case, I have 2. 2 is an even number. 2 even, right? 2, this is an even number. So then we are going to have always double that number. If it's even, you double it. So if that was 4, you make it 8. You're going to get 8. Here we're going to get 4-leaved roses. That's how we call them, 4-leaved roses. So it's going to go in the first one, in this one, in this one, and this one. So those are sine always, sine double, like sine 2 theta, 4 theta. If it was 4, it would be 8. So you will have 2 roses or 2 leaves in each quadrant. But they're going to be in the middle, almost in the middle. So that's for sine. If it's 3 theta, you're going to have 3 roses, but we don't have to do that for now. I just want to talk about the even ones. Same thing happened with cosine. So it's going to have double the even number, but the cosines, they go on the axes themselves. So it's going to have double that. We're going to double it to get 4. So it's going to be 4-leaved roses. So they come on the axes. So they go like this, 1, 2, 3, and 4. But are they identical? Yes, they don't look identical like the way I drew them, but they are. They're supposed to be identical. Now the other thing is, how big is this rose supposed to be stretched out? Well, it depends on the number in the front. This number was 1, so I went up 1 unit. 1 unit for each. 1 unit. 1 unit. So if I change that number to 2, if I put 2 here, then you extend it out 2 units. So it stretched it out 2 units. Same thing here. This number was 1, so we went 1 unit, 1 unit, 1 unit, 1 unit. Okay, so that's what we have. So this is like a general idea about graphs in polar coordinate, graphing functions or equation in polar coordinates. What do we use those graphs for? Again, this just to give you an idea for those who are going to take pre-calculus later on. You will come across these, and in pre-calculus we add more than just graphing. We're going to learn, we chose students more stuff in depth about polar, and then when you go to calculus, you learn how to find areas of these roses or areas in polar coordinates, and you find the length of the arc of the given curve in polar coordinates. And then in multivariable calculus or calculus 3, you learn how to use it even more and see how powerful the polar coordinates can be when it comes to calculus. So again, this is only just introduction to polar graphs. As you could see, every equation has its own shape when it comes to graphing, and that's what this section is about.